For S1, which is shear force and bending moment, the shear force at any point along the beam is the total force acting perpendicular to the beam longitudinal axis up to the point. The bending moment at any point along the beam is equal to the area under the shear force diagram up to that point. Note, for a simply supported beam, the bending moment at the ends will always be equal to 0.
Hi and Assalamualaikum everyone. I am and now I will show you how to determine the objective one. The objective one of this experiment is determination of shear XX due to point loads and loads. So we have point A, point B, point D or XX, and point C. For case 1, we will place the load 10 Newton between point A and point B. Then we will measure the shear force at point B. Then we will add it 20 Newton and 30 Newton to the loads. Then for each trial, we will also measure the shear force at point B. For case 2, we will place the load at any point between point B and point D. And this is the same step, we will also record the shear force at point B. For case 3, we will place the load between point D and point C. Then, the next step, we will also record the shear force at point B. So, for objective 1, we need to plot two graphs, which are the first one is the graph of shear force against the position of the applied load P, and the second one is the graph of shear force against the magnitude of the applied load P. Next, for objective 2, we will use the previous measured shear force to plot the shear force diagram for each case. The measure of shear force will be positive or negative due to the position of point loads. Take case 1 as example, and we can see that the shear force are determined using the shear force diagram.
For shear force due to uniform distributed loading, firstly, apply at least 3 same magnitude point load next to one another. Make sure the distance between each point load is same. For the case 1, all point loads is applied at position 16 mm apart from each other on between span BD. After that, we calculate the uniform load by using the formula given. And we compare the calculated shear force value with the measured shear force value at section XX. This experiment is repeated by applying 4-point loads. Meanwhile, for the case 3, 3-point loads is used at distance 40 mm apart from B between span AB.
For the superposition or the shear force at the superposition, there's two cases we are going to deal with. And the first case, we're going to place the loads between point B and point C. And the second case, we're going to place the load between point A and point B. For this experiment, we are going to use the loads of 200 gram. And for the first case, the first step is we're going to place the loads between B point and C point, and then we measure the distance between the load and B point, which is 60 mm. And then we obtain the data of the V from the measuring device here. Next, we repeat the same thing, the same step, but with the different distance between B point and the load, which is 120, 180, and 240 mm. For the second case, we are going to place the loads between point A and point B. And then, we measure the distance between point B and the load, which is we set on 40 mm. Then we obtain the value a V value from the measuring device. Next, we're going to repeat the same thing, but with the different distance of loops to B point, which is 80 and 120, and then we obtain the value as well. Okay, after we obtain all the experimental data, and then we compare with the theoretical value.
There are three cases of the bending moment variation due to the variation of fluid and the position of fluid. For the case 1, the fluid load of P is placed between point A and point B. For the case 2, the fluid load P is placed between the point B and the point D. And lastly, for the case 3, the fluid load P is placed between the point D and point C. After that, measure the shear force at the SS section for the all three cases. Then, plot graph relationship between bending moment at section SS and position of load P. Plot another graph relationship between bending moment at section SS and magnitude of the load P. Finally, plot shear force diagram and bending moment diagram to show our maximum sagging moment and maximum hugging moment have equal absolute values. First, put a load W at point A. Then we need to select any position to put the load P. For my cases, I choose to put the load P at point C and point D. And then we need to measure the distance between load P until the point B. Next, the load P is determined by using the formula of P equal to 65.33 times by W divided by distance between load P until point B in mm. Then, the bending moment at the SS section is compared with the theoretical value and the experimental value.
Next, for the sixth objective, we will determine the bending moment due to uniform distributed load. For this experiment, we will use as many loads as we can and put it at one point. For example, I will put all the loads between point B and point B. As you can see, all of these loads have the same magnitude and are placed beside each other. The second step, we will need to calculate the uniform distributed load using this formula. The third step, the bending moment was calculated at XX section. Lastly, we will compare the value of bending moment of experimental and theoretical value.
In superposition, the value of loads, if we put the loads at here, here, here and here, will equal to if we put the loads together like this and here. This is what we call superposition. The second case is when we put the loads here and then here and then here will equal to the load if we put that together like here and here. This is what we call in superposition.